both the organizers for the invitation to give a few lectures in this workshop. So my lectures are on supersingular representations of the group GI2F. So we are now going back from the complex setting to FP bar setting. So representations over FP bar, modality representations. And again, I am going to concentrate on the group GI2F. These set of lectures we will try to construct supersingular representations. This word was introduced by Professor Shalini yesterday with some nice properties. So let me begin. I will try to go as slow as possible, but I won't be able to give them all the technical details, but I hope to give you ideas. So let me introduce the notation first. So F. So if it will denote non-Archimedean local field of with field, finite field with q elements. So before that I have to fix a prime number. So let P be a prime number. And this residue field is of characteristic P. So Q is some P power. So what is a non-Archimedean local field? So field of p-adic numbers is the basic example, but I am also going to allow local fields of positive characteristic. So if characteristic of f is 0, then f is called p-adic field. So that means f is a finite extension of p-adic numbers. And if characteristic of f is p, it can only be either 0 or p. Then f is of the form of power series in one variable with coefficients from this residue finite field, and we also allow finitely many negative powers of x. So this is the fraction field of the usual power series in x. Right, and then let me also fix the usual notation. So O will denote the valuation ring. So this is, yeah, so I mean any such a field is equipped with a discrete valuation, and then this O is the subring of all the elements consisting with positive valuation. So for QP, this is the GP p-adic application. So, and we also fix a uniformizer, which I will denote by this symbol. This is pi, some variant of pi. So fix a uniformizer. So this corresponds to the prime number p in QP. So, right, and so what are the objects that we are interested in my lecture? So we are interested in the category, or I will just write that smooth, irreducible, admissible representations of invertible matrices with entries from this local field F 2 by 2 on FP bar vector spaces. So by now I guess everyone is familiar with this adjective smooth admissible. And again, I want to emphasize that we are again now over FP bar, not on C vector spaces. So yesterday in the first talk, the setup was F was QP, and we saw some examples of smooth admissible representations like principal series. And also in the morning lecture we saw another example that was Steinberg over C, but it also makes sense over FP bar. So in this set of lectures we will see whole different types of representations which are super singular. So let me introduce more notation. Yeah. So okay. So the notation. So see, I'm going to fix my group. Then this contains a maximal compact subgroup, but we fix a standard maximal compact subgroup. So this is Gi2O. Okay. So all 2 by 2 matrices with entries from this valuation ring and with the determinant which is a unit in O. And then inside K we have some special compact open subgroups which we have come across in many lectures, but let me just write them again. So K contains with the again containment. So K contains this Ivahori, which is of the form of O star on diagonal, here O and here pi O. Then I has a maximal pro-p subgroup which is denoted by I1. This is called the pro-p Ivahori subgroup. So this is of the form 1 plus pi O, pi O, and 1 plus pi. And I want to introduce one more subgroup which is sitting inside this K I1, which is again a pro-p group denoted by K1. This is nothing but 1 plus pi O. So this is this K1 is a maximal pro-p group inside K, and I1 is a maximal pro-p normal subgroup inside I. So normal in maximal pro-p normal subgroup in K. K1 is normal in K and I1 is normal in I. Right. And let me also write Z for the center object. Okay, so I'm going to state one theorem from Bartholomews paper, and I guess this will be stated tomorrow in Shalini's lecture again, but I want to use this theorem, so I have to, so basically this is about the classification of all smooth irreducible admissible representations of Gi2F. So this theorem says that, so let representations, let me write pi for the representation. So Bartholomew says that pi occurs as a quotient of some representation. So again, this object was mentioned in one of the lectures yesterday. So what is this representation? Every such a representation here, pi, occurs as a quotient of pi sigma lambda chi, where pi sigma lambda chi is given by you induced from the subgroup Kz to G of irreducible representation sigma of Kz. Then go modulo the image of certain operator acting on this, so which was again mentioned by Professor Gate yesterday in his lecture, and then tensor this with character. So let me write here for some irreducible Kz representation sigma, some lambda belonging to Fp bar, and some chi from G, or it will be from F cross to Fp bar cross. Okay, so this is yeah. So to understand all irreducible admissible representations, one needs to look at these kind of objects. And what Barthel and Lunet did is the following. Not only this, but when lambda is not equal to 0, they classified all quotients, irreducible quotients of pi sigma lambda chi, and when lambda is equal to 0, they proved the following, so which I will write as a fact. So pi sigma 0 chi, suppose my pi occurs as a quotient of this represent pi sigma 0 chi, that means lambda is 0, if and only if pi does not occur as a subquotient of a principal series. Okay, so maybe.
So when you mean subjects to pi, you mean that pi is some quotient of your pi of sigma comma 0 comma.
Yeah. So I have okay, so so given a irreducible representation, let's say admissible, of Gn to F, it occurs as a quotient of pi sigma 0 chi, if and only if it does not occur in a principal series. So okay, maybe just to introduce another terminology. So there in the complex world, these representations are known as supercuspidal. So IE is supercuspidal. And since they couldn't classify representations which occur as quotients of pi sigma 0 chi, they were mysterious at that point, and they called them super singular. So let me write on the right hand side, IE pi is, there is a better reason why these are called super singular, but I don't want to mention that, but this you can take as a definition. So super singular representation of GL2F is going to be smooth irreducible admissible representation which occurs as a quotient of pi sigma 0 chi. And what this fact says that pi is super singular if and only if pi is super cuspidal. Okay, but then the question still remains, what are these representations, right? Okay, so then we have this theorem by Roy, another fact. So Roy proved that when F is equal to QP, these kind of representation themselves are irreducible. So, okay, so this means that for GL to QP we now have a classification of all smooth irreducible admissible representations on FP bar, and with Pascunas, Roy and Pascuna also showed that this miserably fails when you replace F by just degree 2 extension of QP. So Roy Pascunas, F equal to, let's say, QP square. So again, recall that QP square is the degree 2 unramified extension of QP. What they show is that this kind of representation pi sigma 0 chi is not irreducible, but in fact this has infinite length. Also feel free to ask if some word is not clear or something. So infinite length meaning it is made up of infinitely many irreducible representations. Okay, then the question is, when F is not equal to QP, what are these objects of interest? Okay, again, when when F is any local field, we know that if the pi is not super singular, Barthelin have classified those kind of representations, but if pi is super singular, even for QP square we don't have any nice way to parameterize or organize all super singular representations. Okay. And maybe to give you some motivation why one is interested. So here in this fact I said that pi is super singular if and only if pi is super cuspidal, and these super cuspidal representations should correspond to irreducible Galois representations on the Galois side in the local Langlands program. So it is very important to understand what super cuspidal representations are.
Is this known to be completely reducible with infinite length, or
What do you mean by completely reducible?
can be decomposed into irreducible, or it is indecomposable?
It is, you mean the Sokal is just one irreducible or something?
Yeah.
No, that is not true.
Can we write it as a direct sum of?
No, you cannot. Yeah, it is indeed. Oh, okay, yeah. I think Arindam has, I suppose, one result, right? So it is indecomposable. Yeah, it is indecomposable, but that doesn't mean that the Sokal is just one bit. Yeah, that maybe that's a. Yeah, I will just write. Although it is not irreducible, it is still indecomposable, and okay, let me write. Is indecomposable. This means that you cannot write it as a direct sum of two sub-representations. And one way to see this as you look at the endomorphism algebra of this. If it is just the scalars, then it would imply that it is indecomposable. Alright, so maybe just whatever I said, I just write it down. So classification of supersingular errors. G. It's not known if my local field is different from QP. So goal here, goal of these lectures is the following. So ideas of. So here I mentioned one result of Roy Pastunas, but in the same paper they do construct families of irreducible supersingular representation, and the goal is to explain those ideas, how to construct supersingular representation. I mean, forget about the classification, even the construction is an important question. Okay. Right. So now I want to begin with explaining this work of Brown Pastunas on the construction or the existence of supersingular representations for the group GI2F. So yeah. So how does one construct? Source to construct representations is look at some set on which G acts. If that set is some nice geometric object, then you should expect that the representation is admissible. It has some better, nice properties. So we have already seen one example of a geometric or graph theoretic object attached to the group GI2F yesterday in Professor Ghati's talk. So that's the Brouhard-Kitts tree. So yeah, so let me recall the semi-simple Brouhard-Kitts building attached to GI2F, which is a tree attached to this group GI2F. This is a tree, and with vertices again are in one-to-one correspondence with the group, with the set G mod KZ, the cosets of KZ in G, and edges are in one-to-one correspondence with G mod. Okay, here I am going to, I am not saying that they should be directed edges, so I am taking something called N, where what is this N? So if recall that if it was oriented edges, you have this G modulo IZ, but this, since you can have two orientations on a given edge, this N is N contains this IZ as a index to subgroup. So this N here is the normalizer or normalizer of I in G. Okay. And so again, as yesterday, I will maybe just to I will draw this tree for p equal to 2, just a few edges, and also to fix some notation. So I have a one edge whose vertices I will denote by sigma 0 and t sigma 0, and so I will explain what sigma 0, t sigma 0 are, and then each edge has degree 3 when p is equal to 2. So let me just draw some edges here. And the standard, this edge joining sigma 0 and t sigma 0, I will write this edge as sigma 1. So, okay, so sigma 0 here is the lattice O direction O, okay, inside f direction f. And we take this lattice up to a scalar multiple, so the class of this. Okay, T was the element beta in yesterday's talk, which the anti-diagonal 1 pi. What does T do here? If you consider T square, it is diagonal pi. So it takes basically T is T fixes this edge, but it reverses the orientation, and we are including this T in this N normal. And sigma 1, okay, sigma 1 is the edge joining sigma 0, so you can compute that this T sigma 0 will be the lattice O direction pi O. And actually this I will sorry, I'm going to change the notation here. So this let me first write that k sub 0 and k sub 1, this is going to be the stabilizer of the standard vertex. So this tree, as I said, that this is some geometric object topology on which my G acts, and maybe so maybe it would be interesting to first understand this kind of object. So G acts on this tree, so stabilizer, it acts, meaning it acts on each vertices and acts on every edge. So stabilizer of sigma 0 I will denote by k0, and k1 stabilizer of sigma 1, the standard edge. And then these vertices will be in the one-to-one correspondence with G mod k0, and edges will be in one-to-one correspondence with G mod sigma, G mod k1. Both these are, yeah, so this is nothing but k and the group generated by diagonal pi, and this is nothing but I semi-direct with the group generated by T, so T power. And so note that both these are compact open subgroups of G. Okay, and also note that their intersection is the group which we came across yesterday. It is the stabilizer of edge together with a direction. So k0 intersection k1 is I. So this is a okay. So let me write one fact which is easy to prove. So given any vertex tau 0 and an edge tau 1 of the tree, there exists G in G such that you can obtain this tau 0 by applying G to sigma 0 standard vertex and tau 1 by applying G to sigma 1 standard edge. Right. Okay. So this. Okay. So how do we? Right. I mean, this is all okay. How do we construct representations of G from something like this tree? So the idea is to. So these are compact open subgroups, right? The stabilizer of sigma 0 and sigma 1. This K0, K1.
This G may be different, right, for sigma 0 and sigma.
No. That is the point. The same G will take sigma 0 to tau 0 and sigma 1 to tau 1.
Any edge in any
Yeah,
vertex.
same. Yeah. Sorry. An edge with vertex tau 0. Sorry. Given any vertex tau 0 and an edge t tau 1.
Adjacent vertex maybe. Yeah.
Huh?
Adjacent. With one vertex tau.
Yeah. So an edge tau 1 having tau 0 as vertex. Thanks. Yeah. Thanks. Okay. Yeah. What I was saying. Yeah. So we have these two. We have these compact open subgroups, and we want to construct representations of G. So first we consider representations of these compact open subgroups. They should be easy to understand because we are in the smooth representation category. Any smooth representation of a compact group factors through finite. Okay. So let's consider a pair. Consider a pair D0, D1 of smooth representations of K0 and K1 respectively, together with a map So you can think of this as a map kind. So I am attaching one representation to the stabilizer of edge and one representation to the stabilizer of this standard vertex. And this map you can think of restricting from this edge to this vertex. So this goes from D1 to D0, D0, and we want that this map should be equivariant or equivariant for the action of K0, K0 intersection K1. Okay. So this is, let me now let's now call such a thing something. So this kind of data we call a diagram. So we call such a diagram. So the diagram is nothing but so diagram D, which is nothing but a smooth representation of K1, D1, smooth representation of K0, that is D0, and a map R, which should commute with the actions of K0 intersection K1. that is IZ on that pole. Okay. Okay, now so given a diagram D, so that this data, so I can consider now compact induction, small I and D. I'm using the notation of Shalini. So this, I will induce my D0 from K0 to G, okay, K0 to G, and I will also induce D1 from K1 to G. So basically what I'm trying to do here is that we have a representation attached to the standard edge and standard vertex. Now I am basically translating that representation to every edge and every vertex. This is sort of this compactly induced representation captures this thing. So okay, I will be more precise, but so consider these two representations. And okay, we have a map. So let me write it. So here, int K0 to G D0. Let me so forget about this tensor with some epsilon. But we have a map from this induction. So I just take the smaller subgroup to be the K1 intersection K0 of D1. So okay, this is clear because by definition, where this epsilon I haven't mentioned, but this character is trivial on this intersection. So you don't have this epsilon here. From here, I have a map which is given by this R, induction from K1 intersection K0, now D0 to G, right? So this will be int of R. And now I want to go back from here to here. So yeah, so I will write this as induction as K1 intersection. I will split this over K0. So this is same as K0 of D0. Induction K1 intersection K0 and induction from K0 to G of T0, and then you have a map like this. These maps are clear. So let me just write what is this epsilon. Epsilon is nothing but character which factors through K1 intersection K0 to. So this is a degree 2 subgroup, and I am taking the non-trivial character. Non-trivial character. So again, maybe if someone is very specific, then if P is 2, then this will be a trivial character. But in that case, it's a trivial character. Okay, maybe what is this trying to do here? So basically epsilon is taking care of the orientation of edges. That is Okay, so I will call the composition of these maps as delta. This is a, sorry, this is not boundary map del. So everything this can be done in the language of uh, in the language of in the topological language, like so this is some space of one cochains on the tree. This is the space of zero cochains or zero chains, one chains and zero chains, and this is the boundary operator. Okay, is there any question there?
What is this vertical map on the right?
So this is from, you have a map from this induction to D0, that is just by Rubin's reciprocity, and then you just alright. So given such a setup, this boundary map is a map of smooth G representation. So now I take, since I already sort of told you that this one can think of this in the topological language, algebraic topological language. So in it's natural to consider the kernel and co-kernel of this map. So those will be some homology groups. So let me write that H0 of D. So this is attached to the diagram D. H0 of D will be nothing but co-kernel of boundary map, and H1 of D is the kernel of. And both these are smooth representations of G. So we have attached some smooth representations to a data on a tree. So first lemma. So in the situation that we are interested in, this group H1D is going to be 0. So the only interesting representation will be H0D. So this is the lemma. Delta, this boundary operator is injective if and only if the restriction map is injective. So proof I will quickly mention. So one way is clear. If the restriction map is not injective, the boundary map cannot be injective, because here from this diagram. So which direction is this? Is that clear, or just I suppose it should be clear. Yeah. So for the reverse direction, I am going to use the notation introduced by Shadini as well as Professor Gati for the elements of compact induction. So we can recall that so every element is a sum of functions of this type in a compactly induced representation. So this is a function which is supported on KG inverse, and it maps G inverse to V. Okay. So if you unravel those definitions, what does delta do? Delta, sorry, this is delta. I don't, is this called delta or del or del? Yeah. So the del on such a function, I will also maybe to distinguish between two different compact induction K1 from K1 and K0. I will also add this sub K0. So this is actually nothing but GV K1 minus it should be R of here minus G so well this T was the element which reverses the orientation. So again, I mean, if I want to explain this map in the terms of chains, so this is a chain supported on a vertex K0, K0 G inverse, and so sorry.
So delta is a map from induction K1 to G. So probably you want to take G from K1.
Yeah. So yeah. So I was saying that this boundary operator takes one chain to zero chains, right? And so okay, how? Yeah. So again, this boundary operator is G equivariant because so you can actually think of this only on the standard vertex and standard edges, forgetting this G on all these brackets. So what is it doing? If you have a standard edge, which I denoted by this thing, I have some one chain supported on this edge, and I'm sending it to chain supported on sigma 0 and T sigma 0, and those 0 chains, their values on sigma 0 and T sigma 0 are given by the restriction map. So this is actually this is the maybe another interpretation of viewing all these maps. Okay. Chain, which will be, yeah, I haven't really chain supported on edge, meaning yeah, I actually didn't define what are the set of one chains on a tree and so on. Yeah, yeah, these are zero simplices and one simplices, and then so you can consider yeah, so one chain will be basically all the functions from one simplices to no, this is I mean this will be equal to this is very there is no continuity. I mean we are not talking about continuity or so this is just okay, let me so let me so okay, so T so this is, let's say, the notation for my tree, and T sub 1 is the set of all edges, so these are one simplices, and T sub 0 is the set of all zero simplices. Okay, now this object here is nothing but C functions from T1 here I should take D1, but all yeah, that is what I'm thinking here. Okay, so maybe um, do you understand this object? This is a function which are supported on cosets of K1, finitely many cosets of K1, right? Now, what are cosets of K1? They are some finitely many chains, right? Okay, and so this is every element here is a sum of Gi, comma Vi, and where K1 Gi inverse is mapping to Vi. This is this function, right? So basically, I am attaching some element in my D1 underlying vector space of D1 to every edge, finitely many edges. I am attaching some vectors. So that is giving me a function on the set of one simplices of the D. Okay, but when you are in the cohomology, your boundary map goes from lower index to higher index. Here it is going from higher index to lower index, so that's why chain. Yeah. Your question was whether it's a co-chain or chain or
Yeah.
no. These are chain because I am we are going from one-dimensional synthesis to zero-dimensional synthesis, so it's a homology, not cohomology. Where I was, yeah, and then if R is injective, then so if V is non-zero, implies that these RV and R T inverse V are non-zero, and that will imply that this thing will be non-zero, because this is a function supported on two different cosets. Is that clear? So implies is non-zero. But again, one has to prove this for finite sums of these kind of functions, not just for one function. But I will leave it to you to think about. I am just proving it for just one function. Okay, so
Formula we using as an exercise.
which one?
The del of the one.
Yeah, this formula.
Yes.
Yeah, that. Yeah, one can also maybe try to prove it using these explicit maps. But I haven't given it as an exercise. Okay, so yeah, I introduced two representations attached to a diagram or a data on a tree, but in which if we are in the situation that R is injective, only the interesting representation is H0D. And maybe one more fact here. So if my restriction map if this is an isomorphism, isomorphism of IZ representations, or you only need it to be an isomorphism of vector spaces, then this, so clearly again H1 is 0, but then H0D, when you restrict it to K0, is nothing but, can you guess what it is D0, and H0D restricted to K1 is D1. So, okay, let me also try to say what this fact is saying. Suppose I am given two representations, D1, D0 of K0 and K1 respectively, And if I am able to, okay, so suppose I have one vector space V on which there is an action of K0 as well as there is an action of K1, which sort of is compatible with the restriction, then in fact this action extends to G action. This is what the fact is saying. Okay.
So usually with an isomorphism to the I1 invariance, right? Or
Yeah, but this is a very special situation. Usually, I'm coming to that part next. Yeah. So okay, this fact is what saying. Suppose I have a FP bar vector space with smooth actions of K0 and K1. So recall that K0 was nothing but K times Z, and K1 was the normalizer of the Iwavel, right? So these both groups contain IZ. So I have a vector space on which there is a K0 action smooth, K1 smooth action, such that their restriction to IZ action is same. Then these two actions in fact extend to G action. This is what the fact is saying. Because I mean, this, then you take D1 to be V, D0 to be V, R to be identity map, and then this is saying.
you're not filling in the blanks. Say it again.
Okay. Okay, so maybe so let me write. In other words, if we have smooth K0 and K1 actions on a vector space V, we are over FP. Actually, so far I haven't used that the field is FP bar on a vector space V. Then there exists a vector space V such that how should I say this? The action that okay, such that their restriction to their intersection, so their restrictions to K0 intersection K1 is the same. The action such that the action of their restrictions is the same. Then there exists maybe unique smooth G action on V such that extending the actions of K0 and K1.
So how are these two connected?
So if I have such a vector space, I take D1 to be that vector space, D0 to be the same vector space, and R to be the identity map.
Okay, then?
Then this says that H0D is the same vector space D0. And this says that the underlying vector space of H0D is the underlying vector space of D0 and D1, so that is V itself. So this is the, we have, and H0D is a G representation. So we are extending the action of compact open subgroups to the whole group. Yeah, that extension is unique. Yeah, because this is a functorial construction. And
So K0 and K1 generate G, don't they?
They generate a subgroup of determinant 1 matrices.
Determined unit matrices. Determined unit.
Unit matrices, ZP star. There is I know there is a easier way of proving this, but I wanted to maybe introduce these things. So yeah.
Determinant unit matrices is an amalgamation of K0
Yeah.
and K1 over, right?
Yeah, that is the same.
That's a faster way to see this, but I'm
Yeah.
still a little confused. What are you saying? You're not saying things explicitly, you're just saying it's obvious. You're writing two facts, but each one is clear, but what's the connection between them?
Okay, which part is not clear?
Both the sentences are good. What
Okay.
is the connection between these two?
Yeah,
Why
so-
in other words? What's the in other words?
Because if I take my diagram to be just identity from A to Z,
Okay, yes. What is B? Is it G representation or?
we have smooth K0 and K1 actions on a vector space V. We have a some vector space on which there are smooth actions of K0 and K1 such that their restriction is the same. Then there exists a G action on that vector space.
Oh, what is the G action?
Yeah. So what is the G action?
H0D?
Yeah, it is the H0D.
You never said that. Okay.
But why is it
Huh?
so why is the extended action same as the thing you get from
Because the restriction of H0D to K0 is D0.
yes? Why G? Oh, sorry.
H0D is B.
Yes.
So K1 contains the T element, right?
K1 contains T.
So they cannot generate determinant unit matrices, right? That is not a unit. So K1 contains little t, right? Whose determinant is not a unit.
It's the conjugate of K or this matrix.
Yeah. So G is generated by KZ
Yes.
and powers of 1, 0, 0 var pi, right? Because that's the decomposition, right?
Intersection.
Maybe
Dot
K
intersection.
star T inverse KT over I.
Okay. Yeah, but I think that K0 and K1 generate G
No, that is.
because K0 is KZ, right? And if we look at the decomposition, we have a decomposition of G into double
Yeah.
cosets of KZ, in which the coset representatives are
Yeah.
powers of 1, 0, 0 var pi,
Yeah.
but that's just a while element away from little t.
Yeah. So okay. So what I was saying, if you just take K and I, the subgroup generated by these two, that will be the unit determinant matrices.
Okay, but so here in this setup, in this statement that you said,
Yes.
so if suppose you have compatible actions of K0 and K1,
Yes.
then you have compatible actions of the subgroup that they generate,
Yeah, but
and that
it should
subgroup
be,
is G.
Unique, I also want.
Yeah, uniquely, right?
Yeah. It should be.
If you have compatible action, then
Yeah, that is what. What is the question?
so my
maybe-
question is, I
are
think
you- so what is your argument that K0 and K1 generate G?
yeah. So we know that the decomposition G is given by KZ. Is a disjoint union of KZ
Yeah.
powers of 1, 0, 0 pi and KZ, right?
And this thing.
Right.
Yeah.
Now, so K0 is already there. And I'm
Mhm.
saying 100 pi
Mhm.
is while element multiplied with little t.
So
on
you
the
have
right.
this anti-diagonal 1 minus 1 here, so you get that t also.
Yeah. So if our subgroup has t,
Mhm.
and if you just attach t to K0, I think that generates G, right? I mean, you write a factorization.
Yeah, you need to show that the action is well defined, kind of. Even if
That would be given by the intersection condition, right? The compatibility.
that is, but even yeah, is that enough?
I think so. I have to think about it, but it's
Okay, I also. Okay, then we
yeah,
can.
yeah.
So,
So R is a K0 intersection K1 linear map?
yeah, that's the definition of a diagram.
You just said isomorphs of vector spaces here.
But yes, but this is a diagram. If it is isomorphism of vector space, it will be isomorphism of representations. Yeah, I mean, even if all the subtleties are not clear, I hope whatever I am writing is still you are able to follow it. Okay, so let me give these examples, some simple examples of these diagrams. So for the again let me recall that we have a diagram meaning the data of a smooth K1 representation and smooth K0 representation together with a map which commute with the action of their intersection only. So so we can as well start with some smooth representation of G, right? And then in this remark we have already observed that we can consider a constant diagram. So let me write it as K pi curly K. So this is nothing but arrow from pi to pi, an identity map. So here I am considering pi as a K1 representation, pi as a K0 representation, and just the identity map. So this is a constant diagram. We call it as a constant diagram. And by that fact again, the H0 of a constant diagram attached to a smooth representation should give you back the representation. So now let's look at some recall that these K0 and K1 they normalizes some these compact open subgroups of G. What are they? So So this K1 normalizes this pro-P Hawley, and K0 normalizes this first principal congruence of protein K, which I introduced this notation right in the beginning. So like these are matrices which modulo pi go to identity. These are matrices which modulo pi go to upper triangular unipotent matrices. So if I start with some G representation on I1 invariants, so this is the again this notation, I hope you are clear. These are all the vectors which are fixed under this compact open subgroups I1. These are vectors which are fixed under K1. So this has an action of the normalizer of I1, and this has action of a normalizer of K1. So normalizer of I1 is this K sub 1, and this normalizer of K1 is this K sub 0. So we have a representation, smooth representation of K1 and smooth representation of K0, and clearly since K1 is sitting inside I1, I have a inclusion map from pi I1 to pi K1, right? So this is this is the sort of important example of a diagram coming from a smooth representation. So this is so is a diagram, and this diagram contains another diagram. So with a sub diagram where I take this K0 representation to be the same, okay, and so I take K1 representation to be the same, that is I1 invariance of pi, and I take my K0 representation to be nothing but the representation generated by this I1 invariance of pi. And then again I have a inclusion. So why this is inside? Okay, I am saying that this is this diagram is sitting inside this. Why this is? It is clear why this is inside K1 invariance of pi again, right? Because this is the subspace of this thing, and this is stable under K0 action. Okay, and maybe just one line that this construction of H0 attached to a data D is functorial. So
what are the H0s for these two cases? You didn't read them?
yeah, I'm coming to that thing. Okay, so the construction. I did not define, right, so there are many things which I am kind of assuming. So diagrams form a category, so there is, you can talk of objects and sub-objects, but okay, it's easy to say what a sub-diagram is. Diagram is a data, right? You have two representation and one arrow. So sub-diagram will be, you have another two representation which are such that individual are sub-representations of them, and this diagram commutes. Yes. By this property. Yes. Okay. So why should normalizer fix on? Okay, so the construction which takes D to H0D is functorial in D, i.e. if I have two diagrams, so D and D prime, and a map between them, then I get a map of G representations between H0D and H0D prime. Okay, so okay, this map is usually denoted by this kind of notation. So okay, so we have this constant diagram which contains this diagram, right? So then we get a map. So this implies that there is a map from H0 of this diagram, pi I1 invariants sitting inside pi K1 invariants, H0 of this diagram to pi. Okay, and if I start with irreducible, then pi will occur as a quotient of this H0 of this diagram. So if yeah, okay. So yeah, so you have D diagram which is nothing but D1 to D0 and together with a map R, and D prime is another diagram, so D1 prime, D0 prime, R prime, and I am saying I have a map, meaning I have two arrows, okay, phi 0, phi 1, such that this diagram comes. So this phi is basically a pair of phi 0, phi 1. Okay, now let me write one important theorem. So over complex numbers, so over C, the map from H0 I1 invariants of pi sitting inside K1 invariants of pi to small pi, I am assuming pi to be irreducible, is an isomorphism of representations. So isomorphism of representations of G. So here I have to assume that that I1 invariants of pi are non-zero, because over complex numbers maybe there is no non-zero vector fixed by I1, but over FP bar we will always have a non-zero vector fixed by I1 because I1 is a probing. And this theorem is due to Schneider and Schluter. Okay, so this construction of attaching some representation to a data on a tree gives gives you the representation back when you consider this kind of data. This is the theorem of Schneider and Schluter, and okay, why this is kind of important because, as I said, pi is a infinite dimensional smooth representations, but these are finite dimensional objects. Pi I1 invariants and K1 invariants, and again going back to what Carol was saying, in his situation he was considering invariants under one compact open subgroup, but here we consider invariants under two compact open subgroups together with a map. Okay, so this is like sort of one level higher than just considering modules over Hicks algebras. Alright. Now, but since we are interested in mod P representation, what happens over FP? Okay. So the situation is very bad. Okay, I have just written that. Okay. If you again take a pi to be smooth irreducible representations over FP bar and take this diagram or data and consider this H0, this is, we know that this will surject onto pi, but this is usually much very big compared to pi. So what I mean by this? So just to give you one example, I probably won't. We can try this during tutorial, but I'm not sure. So for example, if you take, okay, so this is, I'm writing this equality in quotes. This H0 of such a diagram over FP bar would look like this compact induction from K0 to G of some weight modulo image of the Hicks operator. Okay, this is again, don't take this as a strict equality, but just to maybe say that I already stated that when my local field F is not QP, this kind of object is not irreducible and it has infinite length, right? And by these constructions also H0 of such a diagram will give rise to such kind of objects. So this is usually very big compared to pi. Then what is the use of all this, right? If we are not able to construct irreducible representations from diagrams, what is the use? So for that we can look at even more restrictive class of diagrams. So I have 5 more minutes. I will just end with one definition. So okay, so I said that if you start with some smooth representation, consider this natural diagram, its H0 does not give you back pi over FP bar, but you know that pi occurs as a quotient, right? So maybe we can imitate these kind of constructions and try to find irreducible quotients. That is what I am going to explain next. So for that I have to restrict to some subclass of diagram. So basic, let me define what a basic diagram is. So it will be D1 to D0R is a diagram, okay. Okay, so here we make in which what we are going to do is we consider this K0 representation D0 is finite dimensional, what is? The K0 action on D0 factors through this finite group. So K0, recall that this is nothing but the J2O times group generated by pi, and we have a surjection onto J2FQ. Right, we have a surjection from K to J2FQ. I just let pi to act trivially on D0, and also so this is basically saying that I want this diagonal pi comma pi to act trivially on D0. That is what. And further, third condition, this restriction map R induces isomorphism between D1 to I1 invariants of D0. Okay, so in particular I am considering R to be injective here. Let me just end by writing important one theorem and then I'll show. Okay, so probably this is you may take time and think about it. An example, again, this kind of diagram is a basic diagram. You can, maybe I will just write example is a basic diagram. If the matrix pi comma pi diagonal acts trivially on pi, and okay, why let me end with writing one theorem. So this will be theorem 2. As in, it's not second theorem, but in the numbering theorem 2. This is due to non-Pascular. So, given a basic diagram, D, there exists a smooth G representation denoting by omega, G representation such that T is a sub-diagram of this constant diagram on omega, and okay, there are maybe many things to explain here, but I wanted to write this theorem today. Okay. I think I will explain this next time. but maybe just to briefly tell you what this is saying is that we can embed basic diagrams into some constant diagrams on a representation with this property. And this will be important to construct supersingular representations, which we will see them maybe next lecture. Yeah, after it. Oh, and I didn't say this property, but we haven't come across this notation also yet. So, okay. So what is soak K is, I mean, I can just write it on the. Oh, I will just say that it's a weight, sum of all weights in, that is better weight, sum of all weights, because we know that what a weight is now, direct sum is a direct sum of all weights inside, which are sub-representations, sum of all weights in
What is that kappa? K? Second line right at the end.
right at the end. Yeah, that is, yeah, curly K, constant. Yeah, that the notation I introduced for constant diagram.
But you wrote Y or something. Oh, that was a cap K?
Yeah, it was K.
It looked like a chi before.
Oh, okay,
It's a
okay.
K. I see.
Yeah, so something like that.